Hey guys, welcome to another Kubernetes hands-on training. I've been looking into the Model Context Protocol by Anthropic for quite some time now, and I decided to make a video tutorial on it to solidify my knowledge and share it with the community. Today I'm going to build something that connects two cutting-edge technologies, the MCP protocol and the Kubernetes operators. I hope you have enough time to follow along. Let's dive right in. In this tutorial, we're going to build a Kubernetes operator for managing MCP servers. Before I dive deep into the details, I need to clear some basics. First, we need to talk about the MCP product, its architecture, and basically understand what problem it solves. Why do AI applications use MCP server to connect to their data sources and tools? Then we're going to look at the MCP server operator that aims to automate the lifecycle of our MCP servers. By the way, I forgot to mention this README and all the instructions in it and all the text and the resulting code that we will be building together will be put in a repository. I'll put the link to that repository in the description part of the video. So now let's talk about the MCP protocol. So what is MCP? MCP, or the Model Context Protocol, is an open source standard or protocol developed by Anthropic that enables AI application to connect to external services, tools, data sources that already exist, are running somewhere in the cloud, on-prem, on a server, somewhere, and provide textual context generated out of those tools and services and give that textual context to the AI application or the language model. You can think of it as USB for AI integration. So now let's talk about what problem MCP solves. Before MCP was introduced by Anthropic, when people wanted to connect their AI applications and the language models embedded in those AI applications to their existing tools or systems, they needed to build a custom integration between that AI application and their tool. For every pair of AI application and tool, there needed to be a custom integration. On the left side, you can think of the GPT model from OpenAI, Gemini from Google, Claude from Anthropic, and so on. And on the right side, you have your APIs, your custom tools that you want to connect them to your language model. You want to somehow implement some sort of automation for those APIs with the help of language models. If you had M AI applications and N tools on the right side, you needed to build M by N custom integrations. So what MCP does is that it reduces the complexity of this problem into an M plus N problem. So you still have the AI applications or different language models on the left side, but this time you build a standardized, universally accessible server, an MCP server of your tool, and then you can connect it to either Gemini or OpenAI. Now let's talk about the MCP architecture. Similar to web applications, MCP also follows a client-server architecture, but we have three main building blocks. We have the host, or the AI application, so to say. You can think of it like Claude, Copilot in VS Code or Cursor, ChatGPT, and so on. Then we have the MCP client, which is a software component inside your AI application that maintains a connection to an MCP server and receives the context from the MCP server. And then we have the MCP server itself, which provides context, tools, and capabilities to MCP clients. Those capabilities, or types of context that are provided by the MCP server, are called resources, tools, and prompts. So what are those? Resources, as the name suggests, is a static data or content that just gives the AI application or the language model just some more information, some more useful, relevant information, and helps it generate more useful content. Then we have the tools, which is most probably the most important primitive out of the three, which allows the AI application to perform actions and execute those tools. Then we have prompts, which, as you can guess, is a set of predefined templates for interacting with AI. So let's say if your AI application is about solving certain things or doing certain things, let's say in a specific scope, in finance, in law, in medicine, you can define predefined templates that whenever is needed by the AI application, it knows what would be a good to-do list to get that certain task done. It helps the AI approach problems more systematically. All right, let's now talk about why MCP matters for Kubernetes. Before we answer this, let's zoom out a bit and first answer why MCP matters at all. So as we talked about, MCP enables AI applications to call tools, which, as we saw, are basically wrappers around our APIs and do things on our behalf, which is pretty amazing. But if you want to now apply this tool to Kubernetes, what does it mean? Like, what problem does Kubernetes has that we want to apply MCP on it? Kubernetes is also a ton of APIs. It's a pretty complex orchestration platform. It has a lot of moving parts and it evolves continuously. A lot of those APIs are built as abstractions to hide the complexity of the underlying infrastructure, the developers or the users of those APIs. But in the end, those APIs, this bag of APIs is pretty complex and imposes a huge cognitive load, makes Kubernetes not easy to handle or not easy to digest, so to say. If we build the right primitives in our MCP server for Kubernetes API, we can make MCP query our Kubernetes cluster state, deploy and manage workloads, and so on. So think of workloads, pods, for example. If you want to create a pod, you need to call an API. The pod API from the core API group. If you want to create a deployment or do anything with a deployment, you need to call the deployment API from the apps API group. So all of your operations will have to go through the Kubernetes API. All of your operations are API calls. So we can make AI do these API calls for us. So if we build the right MCP server, we can query the cluster state, we can troubleshoot issues within our cluster with the help of AI, and basically automate operations based on the events and what happens in our cluster. So we're going to start by building a very simple MCP server for Kubernetes, which basically can operate or troubleshoot pods. And then we're going to make that MCP server a first-class citizen in the Kubernetes world, which basically means it's going to turn into a Kubernetes API itself. So we're going to build an operator for it, let Kubernetes manage its lifecycle. So now let's talk about the resources that we're going to build for MCP server. So now let's look at a sample resource that we're going to define for our Kubernetes MCP server. Here I'm using TypeScript and the MCP TypeScript library. The server construct basically is a construct defined or imported from the MCP TypeScript library. It has a method called register resource that we can use to register our resources. A good example for a resource when it comes to implementing MCP server for Kubernetes is the cluster information. So here, basically give it a name and then designate a URL path for our resource. in our MCP server. So whenever the AI application wants to query the cluster information, it calls this URL path of our MCP server. And then we have the metadata block. So basically tell the AI application, the MCP server tells the AI application what this resource is about and what is the output format. Basically use MIME type application JSON to tell AI application that the output is in JSON format. And then whenever the AI application calls this resource or requests this resource from our MCP server, this content is going to be returned. Like we're going to return to the AI application the number of nodes, the number of pods, and the version of our cluster. It is important to note that resources are read-only. So when AI application calls them, they don't have any side effects on the state. In our case, the cluster state. And also they should be idempotent. So which basically means you can call them as many times as you want. The outcome in our case might change because the number of pods or nodes can change. Kubernetes is a dynamic environment, but calling the resources does not have any effect on getting a different result. That's what makes it idempotent, and they don't perform action. So now here we're going to look at the MCP tools. This is a sample tool. As you saw in the resources, there is no input. We just query the state. But for tools, we have inputs. So now we have the server construct. We call the register tool method, and we give it a name, again some metadata, and this time we expect some input from the AI model, from the AI application. And this input has a format, has a schema. It needs to be string, the name, image, and namespace. So whenever we want to create a pod, the base minimum input that we expect is the name of the pod, the image that the pod will be running, and the namespace, in which namespace the pod needs to be created. The rest of the stuff will be assumed by our MCP server. So our create pod takes care of putting the right security context or putting the right resource requests or limits and so on. Whenever the tool is called, a Kubernetes client, Kubernetes API client in TypeScript in our case, will be called to do the actual job, to actually call the Kubernetes API to create the pod. As we see here, Kubernetes API will create a namespace pod with the right image and the right name. And in the end, it returns this content of type text, not application JSON. It will just tell the AI application that I created a pod with this name in namespace. As we see, tools have side effects and they mutate the state of our clusters. And here's an example of a prompt, very similar. Prompts have also a name, a metadata, and the arguments that needs to be basically fed into a prompt. In prompts, MCP does not call them inputs. MCP calls them args or arguments, but very similar to inputs. We have, for example, for this troubleshooting a pod prompt, we have a pod name and the namespace as the arguments that can be replaced in this generic prompt. So whenever, for example, in case of troubleshooting, whenever the AI application decides to troubleshoot a certain pod, it already has a predefined prompt or to-do list how to troubleshoot a pod or where to look into to troubleshoot a pod. So this prompt basically defines if you want to troubleshoot a pod with this name in this namespace, check the status and events, the container logs, resource request limits, and so on. So it gives a very nice predefined to-do to the AI application to approach the problem systematically. All the MCP messages exchanged between the AI application and our MCP server are sent over the JSON RPC 2.0 protocol. So MCP is a protocol itself. Under the hood, it uses this JSON RPC 2.0 protocol, which is a stateless RPC or remote procedure call protocol that uses JSON as a data format. The transports that are supported by the MCP protocol as of now are STDIO, which basically means standard IO or input output. The AI application and the MCP server are both running on the same machine. The MCP server writes to the standard IO, and the AI application has access to the same standard IO of that machine and can receive the messages. Another option is HTTP/server send events, which was initially introduced by Anthropic when they introduced the MCP protocol, which basically means you deploy your MCP server just like a typical HTTP web server somewhere, and then you provide some URL to the AI applications or the clients of that MCP server, and the AI applications can configure themselves to call the remote MCP server. The third option, which is a more modern approach to the HTTP server-side event, is the streamable HTTP, which allows streaming the generated text from the MCP server to the AI application, similar to what we see in modern AI chat environments like ChatGPT or Claude. Next, let's talk about the session, the concept of session in MCP. Whenever the AI application wants to connect to an MCP server, it calls the initialize method of the MCP server, and then the MCP server negotiates its capabilities or communicates its capabilities to the AI application, and basically tells it, for example, I have these tools, resources, prompts, and so on. And it doesn't have to. Then the AI application tries to list what is this MCP server capable of, and this will be sort of a knowledge for the AI application. And at the time of active usage, whenever the language model or the AI application decides to call the MCP servers or for tools or resources or prompts, the call or read operations are performed. And in the end, there is a close or cleanup operation that closes the session between the AI application and the MCP server. MCP protocol is a stateful protocol, which basically means the state of your protocol is the communication or the generated text and JSON and communicated between the AI application and the MCP server. Here's some real-world MCP implementations that are already developed and built by the community. We have MCP servers for GitHub, for automated code operations, Postgres, Slack, Kubernetes, and for file system operations. In case of Kubernetes, Kubernetes has a lot of APIs. You can really think of it as a huge bag of APIs, and it doesn't really make much sense to have one MCP server for all of Kubernetes, because then we are going to provide too much context to the language model, and the researchers show that too much context makes the AI or language models perform worse. So there are Kubernetes MCP servers for the vanilla Kubernetes APIs and MCP servers for third parties. Like there's a MCP server for Argo CD or Flux and so on. And usually the third party tools that extend the Kubernetes API, now to make it easier to manage their own API, they build an MCP server so that you can create, for example, Argo rollouts with the help of AI, or you can perform Argo operations with the help of the MCP server built for Argo CD. So enough with the theory, let's get into the hands-on part. Great, now let us build our first MCP server. Before we do that, we need to make sure that our dev environment is properly set up. For development, we need Node, NPM, and a simple Kubernetes cluster like Kind or Minikube. I'm using Kind. And you need to make sure that your Node version is also 18 or later. So I have all the commands that we need to check stuff or install stuff. And to make my life easier, I've installed an extension on Cursor. You can also install it on VS Code, which basically helps me run the commands easily by clicking on this run button here. So if I search for Markdown, this is the extension that I have installed. You can also install it on your editor. Let's go back to the code. So I'm gonna run this block of bash and see the results. You see I have Node version 2020 and I have access to a Kind cluster, which was created 5 minutes ago. Everything looks good. So let's move on to the next part. The next part, we want to create the structure of our repository. So we're gonna create a directory called workspace and put an MCP lab directory in there and initialize a node module by running that. So if I do that, I have my workspace, MCP lab, and package.json. And there's a shortcoming of this extension. When if I do cd commands in it, it basically does it in a temporary bash session and it does not persist. I have to manually cd into that directory. Cool. Now we need to install the dependencies. The dependencies we need are the MCP SDK, the Zod library for schema validation, and the Kubernetes client library in TypeScript. We also need Express because we're going to build an HTTP streamable version of our MCP server. And we are using TypeScript and we need the types of those libraries for our application to work properly. So I'm going to click on this run button here also and make sure I install all the dependencies properly. And if we move on, we're going to now create a boilerplate package.json for our node module. We're going to create some common handlers for our MCP server, and then we're going to build our MCP servers in 2 different transport modes. We're going to build an MCP server that works with Stdio, and we're going to build an MCP server that is HTTP streamable. And for that, the most important part of this package.json is the scripts directory. We have separated the compilation and start commands of those different MCP server types. So if we basically do run npm run dev, we compile our Stdio server, and if we do npm run dev HTTP, we're going to compile the HTTP streamable MCP server. I'm going to simply run this command again to make sure that I have the package.json that I need. And then I also need TypeScript, a TypeScript config. I'm not gonna focus on the different fields in the TypeScript configuration. It is beyond the scope of this tutorial, but importantly for us is the root directory and source directory. We're gonna, for compiling TypeScript, we're gonna look at whatever is in the source directory, and the outcome of the TypeScript compilation will be stored in the dist or distro directory. So I'm going to run this command and create our tsconfig. Awesome. Now we have all the files that we need for Node and TypeScript, and now we need to create our repository structure or project structure. As I said, we need a source directory that contains basically all of our sources, and we can also create directories for examples or some configurations that we want to apply to our code. Let's just simply run this command, and now we see we have the configuration and examples and the source, basically the repository of our project. And now to make sure that we have all the dependencies installed and everything looks good, we can run this block. So we do npm installed on this package.json and check the versions of the installed packages to verify the successful installation. Also, to check the connectivity to the Kubernetes API and the basic permissions, we can run this block of code. If I've simply created my kind cluster by doing kind create cluster, which basically means the credentials, the kube config I get has the basic access to nodes, pods, and so on. And our MCP server is going to use the kube config, the default kube config of our kind cluster. So it makes sense that to check that our credentials have access to the pods and nodes API. So I'm going to run this, and you see that I have access to a cluster. I can get the pods, I can get nodes, and so on. So we did set up everything in our environment. Now, I'm not going to run this block of echo commands, but basically we did install a Node.js, TypeScript, MCP SDK, and we made sure that our Kubernetes is accessible and up and running. Perfect. Now let's focus on the handlers, or the common reusable shared code that we're going to implement for our MCP server. All right, now we want to build the handlers, or the common reusable code for our MCP server. We need the server class from the MCP SDK. We need the Kubernetes client in TypeScript. We're going to import everything and use the K8 alias for it. And we need the schemas for the primitives that our MCP server is going to support. So we need to be able to list resources, read resources, list tools. Like the AI application needs to first know about all the possible tools and resources and prompts, and then also need to be able to read the resources or call tools or get prompts. That's why we need to import all the schemas from the types of our MCP SDK. And then we need to initialize the Kubernetes client. We create a new instance, and then when we call the load from default, we're going to use the default kube config that exists on my machine. Kube config that has the API server address in it. It has the context set and the credentials that is going to be used to talk to a certain API server. So we're just going to simply load it. Then we're going to instantiate a Kubernetes client for the core group to create pods and so on, and the Kubernetes client for the apps group for deployments. All right, now let's look into the resource handlers. As we said, the MCP server supports 3 different primitives: the resources, the tools, and the prompts. For us to enable our MCP server to support these, we need to register handlers for different types of primitives and the different methods that can be run on those primitives. So the AI application might reach out to the MCP server and ask for the list of resources that the MCP server supports. Whenever that's the case, the server needs to have a proper handler for that. So when the AI application tells the MCP server what are the resources that you provide, our MCP server is going to reply, and these are the resources. I have 2 resource types. Basically just returns some metadata around the resources that it supports. Our MCP server can tell us about the nodes in the cluster, and also can tell us about the pods running in the default namespace, the MIME type application JSON. So then the AI application knows whenever it calls these resources, should expect a JSON formatted text that contains information about cluster nodes or the pods in the default namespace. If the AI application wants to actually read those resources, not just listing them, but actually reading information from our cluster, we need to have a request handler for reading resources. One of the things that are specific to resources are the URIs that we specify to uniquely designate the resources. We use the K8 protocol and cluster/nodes, for example, for the nodes. And if the requested URI from the AI application is this, then we're gonna ask the Kubernetes client to list the nodes and then use the map function to create a properly formatted nodes JSON object. And then we're going to stringify this nodes object and also put the number of nodes in JSON string and return it to the AI application. And in case of error, we're going to return the error message that occurred during this operation. For the resource of reading pods, the URI starts with /namespace and then comes the name of the namespace and /pods. If there is no namespace provided by the application, the MCP server will assume that the AI application needs to know about the default namespace. Very similar. It just forwards this information to the K8 API or the HTTP or the Kubernetes client, lists the namespace pod of namespace that was extracted from the URI. Again, create a nice map and then stringify this generated map and return it to the AI application. And in case of error, just propagate this error back to the AI application. So I'm just gonna run this for now, very simple. As you see, the core logic is done by the Kubernetes API client, and MCP is just a wrapper on an existing API. So I'm gonna run this now. And now in our handlers, we have the handlers file. Now let's talk about the tool handlers. Similar to resources, the AI application wants to list the tools that the MCP server provides. Whenever such request comes in, the MCP server should have the proper handler for it and should return some metadata around the tools that it supports. Most importantly is the input schema. So the MCP server should let the AI application know if it wants to call a certain tool, what inputs it should provide. And this is the context that is written. So the MCP server tells the AI application, if you want to create a pod, you need to provide name, image, and namespace at least. And name and image are absolutely necessary. If you do not provide the namespace, I'm going to go ahead and create it in the default namespace. We have another tool, get pod logs, simply looks at the logs of a certain pod in a certain namespace. Again, the required input is going to be the name of the pod, delete pod, list pod, and so on. Very simple, just some metadata around the tools that the MCP server supports. So now if the AI application wants to actually call the tools that the MCP server provides, it needs to send its request using this call to request schema. The MCP server can extract the incoming input from the request. For example, if the create pod is called, the AI application then creates a default pod manifest. You see these resource request limits and so on are hard-coded. It gives this manifest, generated manifest to the Kubernetes client, and the Kubernetes client is going to create a namespace pod and return the result of that operation as a text to the AI application. It's either successful or it's a failure. Similar to creating pods, we have an operation or a tool for getting pod logs, deleting pods, listing pods, and so on. Very simple. You can just go ahead and look at the logic of the handler for the tools. I'm gonna simply run this block to add it to our handlers file. So now let's talk about the prompt handlers. Very similar. The AI application should be able to list the existing prompts supported by the MCP server. The MCP server tells the AI application that it is capable of troubleshooting pod or optimizing resources and returns the proper metadata. And most importantly, it tells the AI application that these are the arguments that are needed for this prompt. And if the AI application actually decide to use those prompts, the request will come in with the get request schema. And for example, for troubleshooting pod, we have this well-defined prompt that can be used to troubleshoot pods. There are certain places that the MCP server can look into to troubleshoot a pod. This nice prompt or to-do list is something that can be given to the AI application upon request, and also for the optimized resources, very similar. When the MCP server wants to optimize the resource, it needs to look into certain places and then make some suggestions. And then now we have this function, this helper function for setting up all of these handlers. So we have handlers for listing and reading the resources, listing tools and calling the tools, and listing and reading the getting the prompts. I'm going to simply run this block of code to add all the handlers to our handlers file. So now if we scroll down on this file at the bottom, we should be able to have everything we need for our MCP server. So we have all the reusable blocks for our MCP server. All right, we created the handlers for our different MCP server primitives, the resources, tools, and prompts. And we also have a helper function for setting them up on an MCP server. So this function gets a server instance as an input and will go ahead and set up those, register those handlers on that server. Now we want to create our Stdio MCP server first and test it locally. We need to again import the server class from the MCP SDK and the stdio transport, and our helper function for setting up the handlers from our k8s handlers file. We have a function here for creating the MCP server. We're going to create a new instance of the server, give it a name and version, and for now the capabilities are going to be empty. And then once we call the setup MCP handlers and pass in our server instance to it, that function is going to attach those handlers that we created to our server instance. And in our main function, we're going to create this MCP server instance and create an instance of the stdio transport and connect our server to the stdio transport, and then log the successful creation of the MCP server, or if there's an error, just write something to the console and exit the process. So I'm going to create this server file now in the servers. As you see, it's in the k8s, it's in the servers directory called k8s MCP server. And now we need to compile this. So I can simply do npm run build, which will call the TypeScript compiler for me, and the outcome of this command will generate the JavaScript files out of the TypeScript that we have. Most importantly, we have this k8s MCP server JavaScript file. Now I want to test the Stdio MCP server that I have created. I'm already using Cursor. Cursor is a well-known AI application or AI host, which can be configured to work with custom MCP servers. If you want to let Cursor use your custom MCP server, you need to let Cursor know about your MCP server and what command is needed to run it and so on. So you need a similar type of configuration for your MCP servers. If you want to manually navigate to this configuration file on Cursor, you need to switch to the Agents tab and then create a new chat. And in the chat window, you need to go to the chat settings, and in the tools and integrations, you can add a custom MCP. I'm just going to simply copy and paste this thing, the readme.json, and I let Cursor know that I have a MCP server called Kubernetes, which can be run by doing node this file, and accepts this file as an environment variable and puts it in an environment variable kubeconfig. Now, if I look at my Cursor settings, I see that it immediately identified my MCP server, and it realized that my MCP server is exposing 4 tools and 2 prompts. Amazing. So let's just do some demo. For now, I'm going to make this terminal a bit bigger and open up K9s to look at my Kubernetes cluster. I have I created a kind cluster. My cluster is empty. There's nothing in it. If I go to the default namespace, no pods running. I'm going to test this by asking AI, which is now equipped with my MCP server, what are the pods, or list the pods. And when it tries to list the pods, it is going to look at the MCP server. It is going to call the list pods, and it is going to tell me 0 pods found in the default namespace, which is exactly matching the state of our cluster. So now I want to ask it, create a pod with HTTPD image. And now it tries to use the MCP server. It realizes that there's a create pod tool in the MCP exposed by the MCP server. It calls it, it creates the HTTPD pod, and then calls the list pods and tells me that the HTTP pod is created. Awesome. So everything pretty straightforward. The AI is basically interacting with Kubernetes cluster with the help of our MCP server. Now let us do something interesting and create a faulty pod. So create a pod with image nginx2, which does not exist. So then it will create a pod, again with the help of the create pod tool, but then it faces the, like the pod fails with the error image pool, but the MCP server creates it. Now if we want to ask to troubleshoot the faulty pod for us, going to look at the state of the cluster, and now it is going to get the pods, list the pods, and troubleshoot the pod for us. It realized that it is running a wrong image. It goes ahead and calls the delete pod tool and then calls the create pod. And basically, within the tools that it has at its disposal, it decided to go with the delete pod first and then the create pod. There was no tool for setting image or patching stuff. So the AI application tried to solve the issue by using the existing tools that it has available to it. And now we see it just basically got fixed the issue somehow for us. So that is basically a demo of how an AI application can interact with the Kubernetes cluster with the help of an MCP server for the pod API of the core group of Kubernetes. So now let's move on to the next part. All right, we created the Stdio version of our MCP server, and now we want to create the HTTP streamable version of it. We need a web framework. We're going to use Express. We need a random UID generator from the Node Crypto package. I'll get to the reason of why we need a random UI generator in a second. But for now, let's continue. The server class, as we saw in the Stdio version from the MCP SDK, the streamable HTTP server transport from the SDK, and our handler setup function from our handlers file, and this type for checking if the incoming request from the AI application is an initialization request. We create our Express application. We assign the port. We either read it from the environment variable. If not set, we just go with 3001. We enable the JSON middleware for our Express application, and we create an empty map of session IDs and transport. So we're gonna store all the transport in a map, and the key of those transports is gonna be the session IDs, and this ID is gonna be exactly that unique identifier that we talked about here, that is gonna be randomly generated after a session is established. So this is how we define our map. This is how we create our MCP server. Again, a server instance using the server class from the SDK, the name, the version. We declare the capabilities as empty for now, and then we call the setup MCP handlers to attach those primitives to our MCP server instance. Then we create a simple health check endpoint for our MCP server that returns some useful JSON to whoever calls this endpoint. This is something we can use, for example, in Kubernetes as a health check endpoint if we want to deploy our MCP server as a pod to Kubernetes. And then the main or most important endpoint of our HTTP MCP server is the /MCP endpoint, which if we use the post method, like if the client use the post method, it will be about the client to server communication. So the initiation of the communication, if it's a post method, is going to be from the AI application or from the MCP client to the server. So here we need to read the headers of the request. If there is already a session ID coming along the request header, that will be extracted, and the server checks whether the session ID is empty or not, and also check if that for that session there is already a transport in our map of transports. And we'll look up that transport if such transport exists. Otherwise, it's going to create a brand new transport for that session. Let's give it an ID using this random UUID generator, and also register the event handler. So when the session is initialized, that transport that was created here will be added to the map of transports that we maintain in our MCP server. And on transport unclose, like we register also the unclose event handler. If the session ID attached to the transport is empty, like if the client wants to actually close the session, the transport should be removed from our map of transports. Here we create the server, and we connect our server to the transport that we just either looked up or created. And if something goes wrong, we return the message to the AI application. Otherwise, we're gonna we have the transport and we have the application running. Now we can let our transport handle the request received by our Express web application. This was for the AI to MCP server communication path. For the other way around, which is called server to client sort of notification or server-side events, we need a get method for our MCP endpoint. How's that gonna work? Imagine the server or the MCP server wants to notify the AI application of something that happened inside the server. For example, in case of a Kubernetes MCP server, some events in the cluster or some logs showing up, something basically that we are basically interested in, and wants to notify the AI application. The AI application or the MCP client will call the get endpoint. It will establish a session already, and then the MCP server will already use the existing transport to send messages or propagate messages from the server to the client. So this method is used to look up an existing session for server-side events. And if there is such session, we look it up and let it handle the request. And here, when the session is about to be terminated, like the AI application wants to actually close the session, this, as you can guess, calls the MCP endpoint with a delete method and extracts the transport and let that transport handle that delete request. And the transport actually then will go ahead and here delete the transport from the map of transports when the delete session deletion request is being handled on close event handler. Now here we have the main function. We start the application by listening to the ports that we specified, some logs, and nothing special. I'm gonna go ahead and create the MCP server. Now we have the MCP server in here. If I want to test it, just a quick check if I can compile it and run it with Node. or import it with Node. I see that I get green check marks. If we want to test the endpoints that we created for our HTTP MCP server, we can also run this script. It's simply gonna start a start HTTP script that we have for our Node application and use curl to do health check testing. Very simple. Let's do this. Again, we see that the health check is working. We're receiving an expected JSON. And that was it with the MCP server manual testing. If we want to test our MCP server in a different way, Anthropic actually has built a very nice tool called Inspector, which you can use to troubleshoot or inspect your MCP servers. You can simply start Inspector by running this command and then pass as the argument your MCP servers. This is for Stdio. For HTTP, you can run the inspector command and pass the URL to your MCP server. So you can just inspect your MCP server simply by passing the URL. I'm going to go ahead and test my Stdio and HTTP MCP servers using Inspector with the script now to see basically how it looks like. If we see that like Inspector managed to hit our MCP endpoint and get some results and so on. Also could manage to hit the health check endpoints and so on, and everything seems to be working as expected. We can also configure our AI applications to use this HTTP based MCP server. I'm not going to go over that for now. Now let's look at the inspector a bit in more detail. I have some scripts in my package.json, the inspector and inspector HTTP. If you want to start the inspector for your Stdio or your HTTP MCP servers. Let me just do npm run inspector HTTP, and inspector UI starts. It establishes a session. I see I have to choose the transport type, the URL of my MCP server, and then if I press connect, I see the initialize method was called by the AI application, which in this case is this inspector environment. And now I have established session to my MCP server. And here I can, for example, list resources. I see I have cluster nodes and namespace pods and so on. I can list the prompts, what prompts I have. I can list the tools and so on. And you can also basically click on this and see the metadata about, you can get information about the input schema and so on. Basically all the details that you need to work with your MCP server, which is a pretty cool tool by Anthropic. So if I now close this, you can also see all my interactions with the inspector has been logged on the console. So if I now go back to the README, we can continue with the different testing setup. If you want to test your MCP servers programmatically, you can definitely do that. Here's a sample test file. It just creates a client. Instead of manually using Cursor or Claude or Inspector to connect to your MCP server, you can programmatically do it and query the tools, the prompts, and hit the endpoints and see what kind of response you can get from your MCP server. Let me just quickly do it. And create this test file. I have this test client now. If I compile it and run it, I see my test is actually successful in terms of calling the MCP server and figuring out what tools and what prompts it offers. So we talked about the MCP server, and the integration with different AI application and simple ways of testing it. Next thing would be to containerize this binary that we are building. We are gonna build the container image for the HTTP MCP server. You need a Docker file for that. In the end, it's a simple Express node application in TypeScript, which I'm going to use this Docker file for containerization of this service. So I'm just gonna run this script, and now I have the Docker file. I can also create a Docker ignore to be on the safe side. These are the commands that I can run to build the image. If I want, I can also test it again, like run the container in a daemon mode, in a background mode, and do the port forwarding and hit the endpoints of health check and MCP and see if I can get the expected results. So let's just do that. Let's build the container and start it, wait for some time, and then hit the endpoints and stop the session. And now we see that we get a green check mark that this tests were successful. This part is interesting. You need to provide a valid session ID to call a certain method of your MCP server. This ID one that I provided was not valid. That's why you see in the request that bad request, no valid session ID provided. For an actual test, if there's already a session established to that MCP server, you can use that ID of that session to perform this testing. If you want, we can also push this container image that we built to some registry. Now we want to move on to the next part and make our MCP server a first-class Kubernetes citizen, which basically means we're going to create a custom resource definition and an operator that manages the lifecycle of our MCP server. We created the MCP server, and now we want to truly make it a first-class citizen of Kubernetes by extending the Kubernetes API and creating a custom resource definition for our MCP servers and a controller that watches for that custom resource and handles the reconciliation events of this declarative API that we create for it. For designing the API, we need to first focus on designing the desired state, the container image that we want to run for our MCP server, the transport type, some port and networking configuration, the number of replicas that we want to have for our MCP server, if we want to scale it up or down, and the resource requests and limits that we want to assign to those pods running the MCP servers. And some MCP server specific configuration, let's say some environment variables that we want to pass to our MCP server. The status part or the observed state have a field for the current phase of the MCP server resource, pending, ready, failed, depending on the situation that happens during the reconciliation event, the number of ready replicas, the endpoint that is eventually callable or reachable in case of HTTP or HTTP streamable MCP servers, and some conditions that are basically detailed information about the status or the observed, and some generated stuff that are written to the status sub-resource by the controller. I'm going to use the Kubebuilder project for creating this API for our MCP servers. If you are new to Kubebuilder or Kubernetes operators in general, please check out the Kubebuilder crash course that I've already created on my YouTube channel. I'll put the link in the description also. I'm not going to spend too much time on the details of this controller. The most important stuff that are related to MCP servers I'm going to go through. So I'm going to now run this block of code to create my MCP operator directory. Now we have an MCP operator directory next to our MCP lab, which contained all the MCP server code. Again, we need to cd into the right directory. Then now we have the project. Now we want to create the API. The API group is going to be MCP. The version is going to be v1 alpha 1. So the fully qualified domain name of our API is going to be mcp.example.com. And the kind is going to be MCP server. We tell Kubebuilder to create a controller for us to watch our custom resource. And a custom resource definition that we're going to need for our MCP server. So if I run this now, I should be able to see that there is an empty boilerplate MCP server API created, which does not have the fields that we want. We're going to implement those next. Now let's look at the API type that we want to implement. As I said, we want to have the image, the transport, the port, the replica, the config, the resource configuration for the pods, some security context for those pods, the service accounts, those pods or those MCP servers will be assigned, and some kubeconfig secret, which is interesting if our MCP server is supposed to manage the state of a cluster that is remote, that the kubeconfig of that remote cluster needs to be stored in this kubeconfig secret, and the environment variables that our MCP server needs. The resources is just the list of MCP server resources when we want to query like kubectl get MCP to get the list of our MCP resources. And the kubeconfig secret ref, which determines the information about the secret holding the kubeconfig our MCP server needs, the name of the secret, the namespace the secret is living in, and the key of the kubeconfig in the secret. And the status or the observed state, you need the phase. As we said, it's going to be an enum of pending, ready, and failed, or terminating in case we delete the MCP, custom resource, the conditions, some details around the observed state, number of ready replicas, number of replicas, total number of MCP replicas, number of ready replicas, total number of replicas, the endpoint to the MCP server, and some observed generation, which reflects the generation of the most recently observed MCP server. And the last transition time is to the last time the condition was changed, like something happened to our custom resource for the MCP server. You can read the comments. It explains what that line is about. The phase, the different phases that we define as a constant, and some string that can be then set to on the status subresource. And most important, the condition types, depending on how the reconciliation loop goes. During the reconciliation, our controller is going to create a deployment, a service, and a config map for our MCP server. If all of this goes well, the condition ready will be written to the status sub resource, which basically means that our MCP server custom resource is ready and our MCP server is ready and usable. Then we have the finalizer. Again, the finalizer route is /finalizer. If you're new to finalizer, finalizer is a piece of logic that handles the post deletion phase of a custom resource. So if things needs to be gracefully shut down, if sessions needs to be closed, or if resources needs to be free, the finalizer takes care of that. The MCP server construct will have the spec and status, the desired and observed state, the list of it, and some helper methods, which is going to be used by the controller if it wants to quickly read some fields from the desired state, and the helper method for setting conditions, which we're going to use in our controller. And some helper method for setting the resources for the pods depending on the transport type. If the transport type is stdio, it is for testing purposes. It's not that important. It's not gonna be deployed into production. We go with minimal configuration. For HTTP and streamable HTTP, we have higher requirements, and that's pretty much it. So I'm gonna run this and update our existing MCP server. And now we have the MCP server type. Now let's look at the controller, which, as we know, the most important function in the controller is the reconcile function. We have all the necessary Kubebuilder markers on top of our reconcile function. Our controller has full access to anything that has to do with our API. It can do get, list, watch, create, update, patch, delete on mcp.example.com resources. And on the status, or on the status sub resource, it has this permissions, and on the finalizer it can add or remove the finalizers. And it can also, as this controller, and it can also manage some sub resources, and those sub resources are going to be deployments and services and config maps and the events of those resources. So with these markers, we just tell Kubebuilder what role-based access needs to be assigned to our controller or the controller manager running our controller. And this is a reconcile function. When there is a request for reconciliation, we need to the API client needs to read the MCP resource from the API. If it's not there, if it's not found, we just ignore it and log in that it is probably deleted. If it is not deleted and it is being created, if the deletion timestamp is null and our custom resource does not contain a finalizer, we add a finalizer to it and update the our custom resource that be with the finalizer being added. And if deletion timestamp is not null, it actually means that we requested Kubernetes API to delete this MCP server, and our custom resource already contains a finalizer. We need to handle the deletion, for example, gracefully shut down the pods and so on. And then we need to remove the finalizer after the deletion has been handled properly. And here we have a function that sets the default resources for our MCP server. If some specs are if some fields from the spec are missing, here's a function that validates the MCP server in terms of configuration, and and requeues the reconciliation requests with some sort of backoff. And here we have some helper functions that we're going to add to the to our controller logic later, which basically reconciles a config map, a service, and a deployment. Just creates those resources or update them depending on what has been given to us via the desired state. So basically reconcile on those resources, and then the update status with the results of the reconciliations. And here's the handle deletion function of our controller, which is called by the finalizer at the time of deleting the resource. It sets the phase of the status to terminating and sets some condition to explain why it is set to terminating. It is set to terminating because the MCP server is being deleted, and updates the status, and then calls another function that actually performs the graceful shutdown. And the graceful shutdown, depending on transport type, applies different configuration, and eventually will scale down the deployment to 0 to shut down the MCP servers for us. You see the different configuration that we have for the grace periods of different transport types. And then we have a bunch of helper functions that are used by our controller either to detect some misconfiguration and return some from the reconciliation loop with some error, update the status depending on how the reconciliation goes. it is pretty self-explanatory. I'm not gonna spend too much time on this. I'm gonna scroll down to the most important function left in this code block, which is setting up our controller with the controller manager. So we're gonna tell the controller manager of Kubernetes that this controller is going to watch the MCP server type resources in the MCP v1 alpha API group, and this controller owns the deployments, the services, and the config maps that are being managed by this controller. So this is how we tell the manager what resources we are watching and what resources we can manage with our controller. I'm gonna go ahead and run this to create the core logic for the controller. If I now open up my controller directory, I have the MCP server controller, which has some errors because some helper functions for reconciling the managed resources, the config map service, and deployment are missing. I'm going to add them next. So for managing resources, we have to have a reconciliation function for deployments, for services, and for pods. And for services and for config maps, I'm gonna go ahead and create those by scrolling down to the bottom of the file and add them. So now we have the reconciliation for deployments. For the services, can go ahead and create them like that. The config map also has its own reconcile function. I'm going to create that for services and config map as well. And now we see that the controller does not have any syntax or compile error. Now it's a good time to try building and making and installing our API on our Kubernetes cluster. What I'm gonna do is that I'm gonna run this block. If I can generate the manifest, alright, the build was successful. And if I do now look at the config crd bases in here, now we see our custom resource definition that was generated after a random make generate. We see all those things that we defined for our spec and for our status are in here with all the necessary validation that was implemented by those Kubebuilder markers and so on. Now let us move on to the next part. We're going to create some sample custom resources in the config samples directory. If we find it here, it's going to be here. So we're going to add the samples for MCP server custom resource in here. Let's just create the basic one and the advanced one. The basic one just has the image transport type, the port replicas, and some config. And the advanced one is more verbose. It has configuration for pods, security context, and some environment variable. I'm gonna run that. And now we have the basic and advanced custom resources, which we can use to test our operator. To install the Kubernetes custom resource definition for our MCP server, we can do make install. And once we do this, the CRD is going to be installed on our Kubernetes cluster. So we see it is created. So if we now do get CRD and grep for MCP, we see it is created, mcpservers.mcp.example.com. Now if I want to run the operator and see if it can reconcile on the sample custom resources that we have, the controller is up and running and waiting for reconciliation events. If I open a new tab, create, for example, the basic MCP server, I see some logs going on in the controller. And if I now, for example, let me open a new terminal and here just do K9S and search for MCP servers. I see I have my basic MCP server pending, And if I look at the reason, it basically means it is telling me that the deployment is not ready. So if I look at the deployment, I see the basic MCP server is not ready. And if I look at the replica set behind this deployment, I see still not so much valid information. Let's look at the pods. I see the pod is failing with error image pool. So it basically means our kind cluster has not loaded our MCP server image yet. I have also put that in the documentation. If you're using kind or Minikube, you need to make sure that you load your Docker image of your HTTP server. That's the command for it. So the image we built for our MCP server is going to be, if you look at the basic, the image is going to be K8 MCP server latest. So I load the image into my kind cluster by running this command. K8 MCP server is the name of our image, and it is what is used in the basic custom resource. I've already deleted the custom resource. If I create it again, I'm not sure. Okay, I need to be in the MCP operator directory. If I create the MCP server resource again and look at custom resource, now I see that my basic MCP server is running. The pod is running. If I look at the MCP server resources, I have the basic MCP server. If I look at the services, I see I have my basic MCP server, which points to the pod, and the container shows me the logs of the MCP server that I have running. And I can look at the status of my custom resource if I describe it. And if I scroll down, I see I have, for example, the endpoint. So this is the fully qualified domain name of my MCP server. And later, if I expose this endpoint via an ingress or gateway, the API applications are able to call the MCP server that is remote to them. All right, so that's it. We covered everything. Once again, we made it to the end of the tutorial. I appreciate your dedication and your patience for following along the tutorial with me. As always, if you liked the video, please give it a like or share it with your friends, and subscribe to my YouTube channel. And also leave your thoughts in the comment section. Let me know what you think about the MCP protocol, specifically in the context of Kubernetes. Until next time, take care.